Okay, now for estimation of heat capacity, if you look on the table B2, the table B2 is based on experimental data. Okay, so they have some experiment and they are using some graph, and then they try to do some approximations, and they have some set of formulations for some substance, right? For several substance that they are get the results from, and then another way to estimate the heat capacity is they have several approximations. The first one we call the Cobb's rule. So Cobb's rule is another way to set up the heat capacity formula. So for example, this is taken from table B10. So CP, for example, CP for the calcium hydroxide. So this will be equal CPA Ca plus 2 CPA oxygen. So they are going to break down into the elements, and then hydrogen, and based on the elements on the P10, we could write to 26. This is 2 multiplied with 17 plus 2 multiplied with 9.6, and the result will be 79 joule per mole degrees Celsius. So this will be the CP. If we compare with real result, real measurement, the real measurement is 89.5. So it's having difference is around 10, right? Around 10. So it's quite, I think quite large if we compare with another rule that we have. So first is Cobb's rule. So they are basically based on breaking down each element, and each element have their own heat capacity, and we can measure through each of them, and we get some. I think if you want for some simplification, I think it's still okay, 79, okay, for some application, but the difference is just 10 joule per mole. And the other method, or maybe before going to for another way, some rules, okay, some rules for approximation. So for liquids and gas, we need to calculate total enthalpy change as the sum of enthalpy changes for the pure mixture components. So later we will discuss this, I think, for a mixing for mixing of system. Later on we will discuss this. This is 8.5. And for this is for mixture, so mixture of liquid or gas. For high dilute solutions of solids, or gases and liquids, we need to neglect the enthalpy change of this solid. So the key is the more dilute, better approximations. And we could say that the Cp for the mixture at some temperature, this is the sum for fractions for each component. So this will be all mixture components. It depends on how many components you have. You could do some summations and make some approximation for the Cp of the mixture. Now this is the, let me write the details here. Cp is heat capacity of mixture. This is, you can use mass or mole fractions. Mass or mole fraction of component. And then this is heat capacity of the component. Okay, and then if we get the Cp of the mixture, then we could just directly go to for specific enthalpy change from T1 to T2, and then this is Cp mixture Tt. Okay. Okay, so another important thing here is, I believe, for the COPS rule is this one, table B10. So if you would like, we could also try to evaluate, estimate Cp for calcium carbonate. Okay, so try to find the Cp, okay, using the table B10, and then basically what you need to do is we need to make this breakdown. So based on the molecules, so 1 calcium, 1 carbon, and 3 oxygens. So 1, 1, 3. So you will have CPA Ca plus CPA carbon and plus 3 CPA oxygen, right? You could try to find this CP mixture. Okay. Anyway, so basically, I think that the essential part is this one. Okay. But for other approximations, this will be from for another section. So this will be focusing on the CP mixture. Okay. Okay. Now, let's see some particular example. Is this? Okay. Okay. So calculate the heat required to bring 150 mole per hour of a stream containing. Now you have a 60% and 40%. So you have different components. And then you have temperature change from 0 to 400 degrees Celsius, and determine heat capacity for the mixture as a part of the problem solution. So the problem is we need to calculate the heat, and the heat we get from the integrations for the CP mixture, right? So first thing is we need to get the CP, okay, the CP heat capacity. We need to get from the ethane and propane. This is from table B2. Check the ethane and check the propane. You will get some long terms for CP, but what you are going to do for that part, okay, you will get this 0.6 or 60% of the ethane. This will be CP. Let me just write ethane, and then plus 0.4. This is CP propane. Okay, the CP is quite long, so you can just take a look at the table B2. So basically, you're going to plus these two according to the percentage, and this will be your CP mixture. Okay, CP mixture. Okay, your CP mixture. And then from those calculations, after you plus these two components, because basically remember the CP mixture is the sum, right? The sum of the fractions and the CP of the components, right? Okay, so basically you need to just plus these two because we know the percentage, and then later on we could check the enthalpy from 0 to 400, and then you just integrate the CP mixture. Okay. And then after we get the specific enthalpy, we could evaluate the heat flow by just multiplying with the flow of the molar flow. That we have the 150 mole per hour, and we could solve this heat flow required, right? And of course, what's the base on all these assumptions, that we assume that it's ideal gas, or you can say close to ideal, that we can justify our calculations to be correct. But I think this assumption should be in your most of the time. Okay, the reasons, as long as there is not no mentioning the conditions, you could just assume with ideal or close to ideal, okay, to simplify the solution. Of course, in real life situations, we never know what happens, so we should have, or we should actually calculate all the possible, all the chances that might disrupt our estimation. But anyway, most of the courses in our lecture, it's going to be simplified. Okay? Okay. So I will just add some notes. Okay. So we've done this is for the mixture, right? The CP for the mixture. The notes that I want to add is the energy balance on a single phase system. So what single phase means that we are not involving any phase change, okay, any phase change conditions. So if the process only involves heating or cooling from T1 to T2 on single species, and the procedure will be as straightforward. Okay, so first is evaluate the internal energy, which is the difference from T1 to T2 of C3 Tt, or we are going to check the enthalpy, which is from T1 T2 Cp Tt, which means we could see that if this is open system or closed system, right? And then closed system is when we have the constant volume, or maybe we can write closed system at constant volume. We could write the delta U as n multiplied with the specific of delta U. And then we have also another closed system, but at the pressure, or constant pressure, sorry. Okay, so for open system, you calculate the delta okay. And then the lastly, substitute all the calculation we get, the delta U, delta H, or delta H flow in appropriate equations, appropriate balance equation to determine the heat, or heat transfer, or Q. Or heat flow. Now, if more than one species, then we need to preparing the table. Okay, input output. Okay, we need to prepare the reference state. If more than one species, or having several inputs or outputs. So first is choose reference state, and then prepare table for the internal energy or specific enthalpy for, okay, and it depends on open system or closed system. And then lastly, the same, we could get to balance the equation and then calculate the heat. Okay. And just to note that what we have in a single phase system. I think I would just go through example to let you see more clearly what we have in a, or what do we do, okay, if we have this condition. Okay. Okay, let's see example. Check the, I think this one. Okay, this is the gas preheater. You have a stream, and we have two components. 10% the CH4, the methane, 90% of air. It's heated from 20 to 300. Calculate the required rate of heat input in kilowatts if the flow rate of the gas is 2 by 10 to the power of 3 liters per minute. Okay, so it's giving you STP, so you could just convert that, and then assuming gas ideal, and you have been given the diagram to help you to observe and analyze. So basically, we could start with the moles. Okay, the moles that we have is 2,000 liters. So we could convert that first to our moles per minute. So we could say that the moles is 2,000 liter per minute. I'm going to multiply with 1 over 22.4, right? This is mole per liter. So we could get 89.3 mole per minute. Okay, so we could write probably the balance equation. The balance equations is the heat flow. We could just write this as our balance equation, and because there's no mentioning any other energy like kinetics, potential, so we just neglect all the small energy. So we could just have this as our balance. So we need to break down this delta H, right? So the delta H is going to be from the outlet minus inlet. So we have the mole and then specific for enthalpy. and an inlet. Okay. And then basically, if we could see that we have the CH4 and air, right? CH4 and air. So we could say that we need to choose the reference state. So choose reference state. Reference state for CH4. That is, what is our temperature? It's from 20 to 300. Okay, I think we could say that the reference state for CH4 is 20 degrees Celsius. It's gas, right? It's gas, 20 degrees Celsius and 1 atmosphere. And for air, it's also gas, 25 degrees Celsius for the STP, and then 1 atmosphere. And we could write down the table, CH4 and air. This will be the mole, the specific enthalpy, the mole, and enthalpy outlet. Okay. Now we could just put all the into the substance. Now based on the percentage, we could take into, so this mole per minute, the total, we could define into this percentage. So we could write here, this is 8.93, this is 80.4. So this is mole per minute. This is kilojoule per mole. Okay. Now the specific enthalpy, this will be 0 as we are going to have the reference state there. And for the air, let's say we have the specific enthalpy 2, or maybe this is 1 first. And then the mole outside, there's nothing changed in the information, so we could just take it the same as the diagram. Okay. And this also the same. And we have the third enthalpy. So because we have air, okay, we could check the table B8 for air. We could check the for the specific enthalpy. I just write in general, so you could check the enthalpy, and especially for the H2 and H3. Okay. Now for H1, if we observe, we have the CH4 for gas, 20 degrees Celsius, 1 atmosphere, become CH4, gas becomes 300 degrees Celsius, and some pressure in an outlet. Okay. So assuming gas ideal, right? Assume ideal gas, right? And neglect heat of mixing. So we could just directly take the H1 is based on the integration from 20 to 300 degrees Celsius of the Cp of CH4. dt, and taken from the table B2, and you could check with some calculations, and this will become 12.09 kilojoule per mole. And the H2 and H3 from table B8, this will be H2 is negative 0.15 kilojoule per mole, and H3 is 8.17 kilojoule per mole. Now from here we could write down the delta. Okay. So the delta will be, or maybe let me write just because we already take these calculations. So we could just plug in all the specific enthalpy into these equations. We could get the delta H as the 776 kilojoule per minute, and then we could exchange to kilowatt. So divide by 60 is around 12.9 kilowatt. Okay, so table B8, table B2, to table B8 for some enthalpy that is given, especially for the air. Table B2 for the CH4. Okay, now similar thing if you have like several streams, basically what you are going to do is take the reference state, take the reference, and then take sometimes to calculate the heat, the enthalpy through the table B2 for the heat capacity, and then sometimes you could also check through if you have a vapor, which means you have a saturated or maybe superheated steam. You could get to B6 and B7, okay, or B5 to B7 for the specific enthalpy, and I think the rest should be equal. Okay? The rest should be generally equal. Right. Now, another segments for the calculation of the integral of the CP. If you remember, we have some numerical method in integrations. Okay, so sometimes you could also check through. So if we have the CP dt, okay, if we have the CP dt, let me go through. This will be functional if CP data is available, right? Okay, in table B2, especially in table B2. Okay, and we could integrate easily. Okay. Now, what will happen if there's no data? One of solutions, we could use some numerical methods. Example, we could check the Simpsons method, if you remember Simpsons rule. Okay. So basically, Simpsons rule is you have the 1, 4, 6, 4, 6, right? And it depends on how many n you have, right? But I think the case when you are using Simpsons rule is just a few, but not really a matter. But this is a valid response for if the CP data is not available. Okay. Anyway, that is just notes, small notes for the heat capacity calculation. Okay. Now another aspect for this chapter 8 is if you have the phase change. So let me write the phase change operations. Okay, now if you have the specific internal energy of liquid and specific internal energy of vapor, which one is higher? Which one is higher? This or this? Okay. So it is the liquid that higher or the vapor that higher for the internal energy? You can type in the chat box. A liquid or vapor? Vapor, correct. Correct, vapor. So I think the best way to understand the concept is through the degree of chaos, right? The degree of chaos of the molecules. If you look at the solid and perhaps a liquid and vapor, like that. So if you could imagine they have movements. The solid is just stay as it is, a molecule, and the liquid it can be moved, but maybe not much. But for vapor, it could move through like really, really high in terms of their randomness, their chaos. The entropy is much higher. You can also argue from that aspect. So we could say it's much more energetic, So from this examples, what I want to say is the phase in some substance is really essentials if you want to compare their energy, okay, their energy for so to transform from the substance when they are solid to liquid or from liquid to vapor, they have some sort of energy to be activated, right? So we could say that this is that's what we call the latent heat. So we could say this is the latent heat. So this is idea of latent heat is basically related to the change of enthalpy, or maybe maybe not change, maybe specific enthalpy change. Maybe that will be better. Specific enthalpy change with a transition of a substance from one phase to another at constant T and P. Okay, so that's why when we are evaluating the pathway or the enthalpy, we need the latent heat becomes very important to give some change in the enthalpy. So one example of this is heat of vaporizations. And also the heat of fusions. So let me write here, this is the delta H having T, okay, and then heat of fusions. This is or melting, we could say that this is also melting. This is delta H and then M. So vaporizations from the terms vaporize. Of course, you can easily see that it is changing from liquid to vapor, and the fusions. This is solid to liquid. Some of the substance we could say that it's already tabulated in table B1. Okay, table B1. If you would like to check, you can check table B1. And usually they will apply for the normal boiling point, okay, for the temperature, and also for the melting point for the fusion. You could also check the temperature they need for melting or for boiling. And at that temperature, they also need the latent heat, okay? So the important thing is the temperature, okay? The temperature of boiling point and the melting point. Okay, that's the first case. Okay. Hopefully I can at least finishing the most aspect in the chapter 8. Okay. Let me go to the next sections. Okay, so how do we apply? Okay. Okay. And let me just continue. Okay, wait. So we discuss until the latent heat. Okay. Okay, let me move to another slides. And giving you more context on this heat of vaporizations. Okay, now we deal with these questions. It's having methanol. Okay, so it's asking how much rate of the kilowatts that must be transferred to a liquid stream of methanol at its normal boiling point. Okay, so it's giving you certain obvious reason for the heat transfer calculation, and they need to generate this 1,500 gram per minute. Okay. So I think we could just focus on the table B1. We get the heat vaporizations, and this is the heat vaporization at this normal boiling point. And we could just directly go to the balance equations, and I think directly we just get the heat transfer that we requirely need, right? So I think nothing that really complicated here. I think the second example that is, I think, need to have much more analysis. So we say the other one is we have vaporization, and we have also the heating. So we need to have several processes in one cases. So here we have the 100 gram moles per hour of the hexane, liquid hexane, 25 degrees Celsius at 7 bar. It's vaporized. After vaporized, it's heated to 300 Celsius at constant pressure. Estimate the rate at which heat must be supplied. So the heat rate, okay, which means that we could start with the balance. Generally, we start with this, with the table B1, checking the delta H for heat vaporizations, which is 28.85 kilojoule per mole. This is at temperature of the boiling is 69 degrees Celsius. Okay. So we need to construct a pathway or construct pathway. So we could say that it goes by from 25 to 300 with several steps, right? We could have the vaporization. We could also have the other changes as well. I think I just could just copy the picture here. The first state is we could have, okay, the state 1 is the initial, our first conditions that we have in the questions, and the state 7 is our final conditions, our final. So we could have the 300 Celsius still 7 bar. Now we could construct a different pathway. So let's say we start with the first one. Let's say from the state 1 to state 2, it goes by to A. So we start with changing the temperature to 69, okay, which means the 69 is our boiling point. So change in the, so T is increasing. And then we could, it goes to 146, increasing again the temperature. This is the true, let's say the true temperature or true vaporization temperature. Okay. But for the table B1, they say that the normal boiling point is 69. So which path that should we follow? Should we follow that we goes through the state 3 and then goes through state 6, change the phase, okay? Or we could go to this C, that is changing directly the phase, and then we get lastly the vapor. Now we could have these several paths, okay, but what we need to construct is the way that we are going to collect our data. It's based on our data. The availability of our data is also our consideration. So if we look at the first is let's say the first steps that we are going to observe is A. So we start with A. I think that is quite possible for the 69. Okay, for the 69 we have the table B1 right at 69 degrees Celsius, so it's possible. And from the 69, because we already described that this is the heat vaporizations, then we could change the to vapor. So we could go to D with some heat vaporizations there, and then from here we could just taking into our final conditions, which is this 300 Celsius and 7 bar. Okay. So I think for availability of the data, and then I think for better calculations, we could just choose the ADG for our path. Because the other path we are not sure, like for this one, this is they said it's through vaporization temperature, but we don't know the exactly what is the enthalpy of that. Okay, so we cannot really figure out the state tree, so we couldn't follow that path. So we go for the ADG because we have the important thing is this delta of heat vaporizations at the normal boiling point. So after that, what could we do is we start finding the enthalpy for A, which is we have two conditions that is changing. First is the temperature. The second is the from 7 bar to 1 atmosphere. So the first thing is we could get the specific volume and then multiply with the delta pressure, right? And then plus the from the 25 to 69 for the CP CP of the hexane. I think you could just go through some table. So we could check the table B1. Table B1 is for the specific volume. We could check the specific gravity of the hexane is 0.659. So we could take that as our density. And then table B2 for our CP. And then we calculate, and we could get this kilojoule per mole. What atmosphere is around 1.013 bar. So we could convert the bar into, or 1 atmosphere to the bar. So we could get the total for the delta H for A. So 1 liter over 0.659, 1 minus the 7 bar, and then multiply with the all the necessary molecular weight, the mole, the gas constant, convert to the and then plus the CP, and then the temperature difference. The total is around 9.44 kilojoule per mole. Okay. Okay, so the second one is the D, that is our heat of vaporization. So we could just take this for accent. This is from the table. We get 28.85 kilojoule per kilogram. We already also mentioned that. And the last one is the G. We could just take the integrations from 69 to 300 CPDT for the, and we could just take the integral, calculate, and we could write this 47.1 kilojoule mole. So I think all the delta H we could just add. Okay, that is the total for the delta H for from the initial state to the final state. And then lastly, we could just take into our calculation of the heat flow. That is just the molar flow multiplied with the specific delta H. And we could get for some kilowatts, and we could just calculate. Okay. Okay, another notes that we could see from our calculations here is if we are having in a closed system, okay, that's can also rewrite the formulations for the closed system. We are going to use the enthalpy equal internal energy plus PV, right? So for a closed system, we could get the internal energy from the enthalpy minus the PV. So that's the way you are approaching the closed system. Okay, so next is just some notes here. So for closed system, because in the closed system we are dealing with internal energy mostly, so we could get the internal energy from the specific enthalpy minus the change in PV. And sometimes in some conditions, for example, for phase change involve liquids and solids, change in PV is negligible, so we could ignore that. So we could say that the delta of the internal energy is not equal, but maybe approximately equal with the enthalpy of the melting. M is for the melting. And for vaporization, this pressure and specific volume for vapor, so usually equaling equaling the RT as we mentioned in the previous calculation. If ideal gas is normally orders magnitude greater than PV for liquid. So it's in the number is really greater than the liquid. So PV is RT, and the internal energy for vaporizations is generally approximate with the enthalpy minus the RT. Okay, so we could say that our PV can be exchanged or substituted with the RT for the vaporization. But for melting, we could just say that it's approximately the same. Okay, now the next section is still we discuss the latent heat, but we have some method to estimate the latent heat. So estimations of latent heat. First, I just go directly for some rules. We could have the Troughton's rule. This will be zero point 0.088 TB and in Kelvin, the boiling point. This is for non-polar liquids. And for the polar one or water, we could use the different formulations. Low molecular weight alcohols. Where TB is the normal boiling point. And another equation is called the Chen's equation. Chen equations is basically for checking the heat of vaporization with some long methods, and it's using the normal boiling point and also the critical temperature. And I don't recommend to memorize this, right? I don't recommend. So TB is normal boiling point, and TC is critical temperature. And PC is critical pressure. Another way to uh, to to estimate the melting or fusions is some equation that we might use. But of course, most of this method, they have a huge gap in the error. So unless the question is asking you to do this method, then I think it's not really accurate. This is for metal element, inorganic compounds, and organic. Maybe it goes a little bit. Okay. All right. Okay, another estimations that we might have is from the Clausius-Clapeyron that you might be aware of from, I think, from chapter 6, right? From chapter 6. Let me move to the next sections. Okay, so let me write again. Clausius-Clapeyron. Clapeyron. That is the ln, the pressure, is equal to negative delta heat of vaporization divided by RT plus B. And we could derive this. And I think you could just use this one, another equations. So derive ln B, derive with respect to this 1 over T is here. So what does it mean is the delta H V can be estimated from vapor pressure data by plotting ln B versus 1 over T. So we could find through the slope, right? Slope of the tangent to the curve. And you may use some different numerical methods to find this this plot of the graph. Okay, to estimate, another point is to estimate the heat of vaporizations at some temperature, like at T2, from known value at T1 is using the Watson's correlation. Okay, this is delta H at T2. and then multiply with where Tc is our critical temperature, as we discussed before. But again, I'm not suggesting for memorization all this formula, but what you need to see is these conditions. Okay? So this is when you are going to estimate the heat of vaporization at some temperature, okay? And you compare with the other value that you have known from at different temperature, right? And you can use this correlation. So this is all this small aspect for the latent heat. That is also one aspect in the total of the enthalpy. Still, the focus, the focus that you are going to be observing is the balance equation in total. Okay. Okay. Now for energy balance on a process that involves phase change, uh, let me just write some notes, and then I think for last 30 minutes, 40 minutes, we could focus on the psychrometric. Okay, psychrometric. So let me write some notes for you. Energy balance. Processes involving phase change. So first, remember to write the reference state. So for some phase temperature and pressure. Okay. Okay, and then after that, calculate the specific enthalpy for all components. And then if a substance, for example, if substance is in the liquid phase at its reference state, meaning the temperature, pressure, you already choose some reference state, and it became vapor, it becomes vapor in the process stream. So the specific enthalpy, you could get these from you could bring liquid from the reference temperature and then bring to a point at which the delta of heat vaporizations is known, as we did before. Okay? So we need to correlate this with the table B1. I think that will be better. So whenever you have some phase change, you could just go to look for table B1 and see at least the temperature. Okay, what is the temperature for some phase change, and you are going to construct your path that way. Okay, I think that will be better. Okay, instead of other way that is, I think, still possible, but of course, according to the availability of the data, I think just taking to direction that the data is available, that is really better. And after that, after we bring this to the point for example, a boiling point, and then after that, we vaporize the liquid, which means it's using the heat of vaporizations. And after vaporize, bring vapor to heating the temperature. Okay, I hope this my writing can be understand. It is the same as we did before. It is the same as we did before. Okay. Which means you need to be careful when you construct the path. Okay. Okay, I think we can go to Psychrometric Chart. Okay, Psychrometric Chart. So Psychrometric Chart is, we could also call that as a humidity chart. Okay. It's a chart that is, let me write here, Psychrometric Chart. Psychrometric Chart. Metric. We could also write this as humidity chart. So it's a chart that is describing the cross plot for a gas vapor mixture, okay, to see whether we could analyze the humidifications, drying, or some air conditioning process. So let me write this is used for analysis of humidifications, drying, and air conditioning process. Let me write some terminologies that we are going to have. We could have the dry bulb temperature. So this is the air temperature measured by thermometer. Any device that could be measured by measuring by temperature measuring instrument. The second is absolute humidity. Sometimes we call this with the terms of HA. This is in the as kilogram vapor over kilogram of DA or dry air. So how much water in the dry air? You could also call this as a moisture content. So if you see from the ratio here, I think it could be understood as well. So if you have like for example 0.0150 kilogram, this means that for 1 kilogram of dry air, there is 0.0150 vapor water. Okay, I think that could be understood. And we could also have the relative humidity. I will give you the chart after this page. Let me just write all the terms we are going to have. Or HR, this is 100 multiplied with the pressure, by pressure at some temperature. So this is it's easily to be described this using the chart, but let me just write this is as the curves on the chart corresponds to specified values, which means the specified values can be understood as a percentage. We will see later in the chart. And then the next one is the dew point, or TDP, the temperature at which humid air is saturated. If cooled at constant pressure. Later we could determine in the chart. The last one, this is the humid volume, or VH. This is meter cube over kilogram dA. This is similar to what we have the moisture in the moisture content, but the content is in the volume. So this is the volume that occupied by 1 kilogram of dry air plus water vapor. And we could also see from the chart. And I will give you one example on how to calculate all these terms. And lastly, we have the wet bulb temperature, or TWB. TWB. So to imagine this wet bulb temperature, imagine you have porous materials. It's soaked with water. Soaked with water. And then you have temperature, thermometer. And you are going to use those porous materials that has been soaked in the water, and you wrap in this thermometer. Okay, wrap. Should be upside down. I mean, should be here. Okay. And the readings of the thermometer will be changed. So the final reading is, we call it temperature of wet bulb temperature. So the difference when we are compare with the normal temperature, okay, it has another water, okay, another stream of water, right? That is, they can have some heat transfer, right? So you will see that the temperature will be have some differences. So the evaporation of water from the porous materials, it will accompanied by the heat transfer from the bulb, and then it will cause the change or drop in the bulb temperature, and then that's the reading. So the reading will be uh, going to be lower. Okay, so imagine this: the air is humid air. Okay. Okay, now let's see what's the chart is about. Let me just go through here. Let me just go through here and giving you the chart. Okay, now if you look here, okay, you could see that it has this wet bulb. Okay, or we could say that the saturation temperature. So how do we uh, start the readings? We could start from the bottom. We could start from the dry temperature, which is the normal temperature that we have measured. Okay, and then it depends on what we have. For example, if we would like to see the relative humidity, see this percentage. For example, we are going to have this 500 not 50% relative humidity. So this line is our 50%. So we could have this line here. Okay, and then if we have, for example, the 25 degrees Celsius for the bulb or the dry temperature. This was what we have here in this line, and we could say that we get the enthalpy. This is our enthalpy, and we could also looking at the moisture what we have here. So if we have the moisture is, for example, 0.006, so we could just take in there, and we could have this as our relative humidity we get. So basically, the way we work on the psychrometric and determine some terminologies, okay, finding the enthalpy, and also finding another aspect as well. We could just go through this chart and take the line, and we need to be aware of the questions. Okay, but I think I will just give you some basic on how do we solve through the question. So this question is at least one question will be appear in the final exam for the psychometric. So you need to be aware on how we could have questions. Okay, let me just go through the question. Use Psychrometric Chart to estimate absolute humidity with bulb temperature, humid volume, dew point, and specific enthalpy of humid air at 41 degrees Celsius and 10% relative humidity, and amount of water in 150 meter cube of air for all these conditions. Okay, so we could start with, let's say we start with the 10%. So 10% is here. This is the 10%. Okay, that is 10% at 41 degrees Celsius. Okay, 41 degrees Celsius. So this is 40 and this is 45. So 1, 2, 3, 4. So this is 41, right? So this will be our 41 degree. Okay. What else we have? Absolute humidity. Okay, absolute humidity. So absolute humidity we could get from the moisture content, the right side. So we could take it into so it's around here. So it's between the 0.004 and 5, but it's close to 5. So you could say you get right some simplification and you say that the humid or absolute humidity HA is 0.0048, okay, kilogram of water over kilogram of PA. Okay, now next one is wet bulb temperature. The wet bulb temperature is, well, so we have this 41 degrees Celsius, right? And then we might have the saturation curve. Where is the saturation curve? This line, the last line is saturation curve. So we could have from here, take a long step through here, okay, the blue line, and we put that goes down the saturation, and we get this is around 19. This 19 is the wet bulb, okay, the wet bulb temperature. Okay, I hope you can follow these steps. So the wet bulb temperature is 19 degrees Celsius. Okay, and then the humid volume. Where's the humid volume? This humid volume, this one, okay, 75, 80, 85, 90, right? So we could say that it goes through, we need to make it a little bit similar, the line, the slope. So it should be goes through here. So it's close to 0.90. Okay. And I think you could just take, because in between this 85 to 90, it's just 0.05. Okay, so probably we could say that because it's close to 0.9, the humid volume goes through by the humid volume, or that's volume specific, is 0.89. Okay, maybe that's will be a best choice for the number. Okay. Okay, and then what else? The dew point. The dew point is the temperature at which the air with the given water content, they are going to be saturated. So we could have the dew point is they are going to have in the saturations. Okay, here's the saturations. We could make this line longer. This moisture. Oh, make a new one. Make with different color. So we need to make it longer, and longer. Make it there. Get a bit longer. Okay. So this line here, because the dew point is the temperature that would be at which the air and the water content, they are going to saturate it. So this 0.0048 will be going to be saturated. So the temperature we need is this. This is 3, 4, right? So it's 3 degrees of Celsius. So that will be the dew point. Okay. And what else? Specific enthalpy. Specific enthalpy for the 19 degree for the wet bulb. For the wet bulb is, we are going to have this this line, right? It's going to be, so specific enthalpy at wet bulb temperature is 54.2 kilojoule per kilogram dA. And then we may have some deviations. So we may have some enthalpy deviations. I forgot to mention this. But I think I will, maybe next week we can have more discussion. So we have the enthalpy deviations also. And it relates to our calculations. So 41 degrees Celsius and 10% relative humidity is our subject. And then the enthalpy deviation will be corresponds to the, if we see our subject, this will be going to be in between this line. Let me write in different color. In between this line, these two lines, because this is precisely the deviations, right? The one that we want to calculate. Let me do this through yellow. Okay. So from there, we could simplify. Again, you need to have more simplification here, that the deviations will be going to be around, okay, around negative 0.7. So the enthalpy will be 54.2 minus this deviation, which is 53.5. And the second question is the amount of water. So 150 meter cube. Calculate with the, divide with the volume. And multiply with the moisture, which is the 0.0048. This is the A. So you could see that this is equal to 0.803 kilogram of water. Okay. So I hope to get the absolute humidity, temperature of wet bulb, humid volume, the dew point, and the enthalpy. This will be depends on the chart. And also in the chart, we have some deviations that might happen, that we need to use these deviations to get the final results of our enthalpy. Okay, I think I will just end here. We will get you to this psychrometric chart for another one example next Monday. And remember, I will announce on the Saturday morning for the quiz. So you just need to prepare. It's open notes. You can prepare notes or textbook if you want. But I think notes will be better. But if you want to prepare books, that's okay. Prepare also the appendix. If you would prepare the appendix through your books, so you could prepare, or you could copy first and then use that appendix. And maybe if you want to write notes in the appendix, that should be okay. I will prepare Saturday morning. just check the Moodle, follow the instructions. Okay, follow the instructions, and I think see you on the next class Monday, and I will just prepare for Saturday and Sunday for working on the how many tests do we have more? Do we have quiz for chapter 8? I think we still have quiz chapter 8 and then final exam, I think. Okay. So this week will be finalized for chapter 7, and maybe next 2 weeks will be quiz chapter 8, and while we finish chapter 9. And I think in the first week or second week of June, before 10 June, we will have the final exam. And probably if it's taken Monday, let me check the possibility. If we have on Monday, then I think yeah, maybe 6 of June or 9 of June, 6 or 9. That will be the final exam. So before that, maybe 1 week before, or yeah, around 1 week before, maybe the second midterm, I will ask Professor Esther. I think she already finished the grading. I will let you know how to contact her or just email her. I will let you know later. Okay. I will ask Professor Esther first. Okay. And I think that will be the end of our lecture for today. So hopefully we can finish the last sections on next week, and we can move to chapter 9.